Question number 1. MOSFET can be used as current control capacitor, voltage control capacitor, current control inductor, voltage control inductor. This came from GATE EC 2001 for 1 mark. Remember, generally 1 mark questions are concept based questions. Concept based. So let me explain. Problem 1, we call it as W1 because W means worked out example. So what we want to say, generally capacitance is given by some constant by root of Vj, where Vj is V0 minus Va. In our case, V0 minus of minus Vgs, because Vgs is generally positive. So what happens finally? Vj increase with reverse bias, because this minus sign is for reverse bias. Therefore, as Vj increase, capacitance decrease. In fact, if you use that, it's all because of junction here. That's one aspect. The other aspect that we have is Ct is epsilon not epsilon r silicon dioxide A by A, epsilon A by D. A is here and D is there. Now what is that? Silicon dioxide layer. Because in the MOSFET, silicon dioxide layer is acting as insulator. So therefore, even in this way, if you increase voltage, capacitance increase. And when you change voltage VGS, automatically the capacitance also will decrease here. Overall, we say this is called voltage control capacitor. Voltage controlled capacitor. Voltage control capacitor. Therefore, among the options given, option is B. B option. Question number 2. The effective channel length of a MOSFET in a saturation decreases with increase in gate voltage, B drain voltage, C source voltage, D body voltage. GATE EC 2001, 1 mark. By this you can say you can have 2 bits. So let us see what is really happening. If you give gate voltage, the effective length of a channel, for example, you have this is your MOSFET and this is your gate. This is called source and you have silicon dioxide layer. In this way you have aluminum. Now what happens is, if you change this VGS gate voltage, gate voltage will create induced channel here. That's called induced channel. This is called length. So length cannot be affected. Length can be affected only by drain. If you see the drain, if you change the drain voltage, we call it as VDS. Some people call it as VDD. Why? Because whatever drain voltage you give is also seen directly across VDS. Therefore, the most possible answer is B, because drain will affect the operation. So let us see the options once again. Gate voltage cannot have effect, but drain voltage can affect. Right. Question number 3. The lower turnoff of MOSFET when compared to BJT can be contributed to which one of the following? The point is, which one is the reason for less turnoff? Less turnoff. A. Input impedance, positive temperature coefficient, absence of minority carriers, on state resistance. This is given in IES EEE 2007. See, when you look at MOSFET, particularly even FETs, in FET, minority current is 0. No minority current. When there is no minority current, what will happen? Suppose you say on to off. Generally what happens in BJT, all this should go back and be stored. When they go back and be stored, such a current, such a time, we call it as storage time. And the next carriers to go, that is called for next carriers to go forward, that is called transit time. So these are the things. So generally the total switching time is equal to storage time plus transit time. Storage time, transit time. Understand? Now here what's happening? No, this is for example majority carriers. For them to come back and next one to go, such a problem is not there in MOSFET because there is no minority carriers at all. That's why, because there is no minority carriers, we can say switching is fast. Can you see the option there? Option is C. Let me read for you once again. Options: A. Input impedance, B. Positive temperature coefficient, C. Absence of minority carriers. So there is no minority carriers, that's why option is C is correct. Next, question number 4. When the gate to source voltage VGS of a MOSFET with threshold voltage of 4 millivolts working in a saturation of 900 millivolts, the drain current is observed to be 1 milliampere. Neglecting the channel width modulation effect and assuming that the MOSFET is operating at saturation, the drain current of an applied voltage of VGS 1400 millivolts is A. 0.5 milliamperes, B. 2 milliamperes, C. 3.5 milliamperes, D. 4 milliamperes. GATE EC 2003. It's given for 2 marks. You know why it is given for 2 marks? Because it is calculations are involved. Let me go one by one. In a MOSFET, this is basically enhancement MOSFET. First thing, he said VT is, the voltage given to us is 400 millivolts and VGS given to us is 900 millivolts. Okay. For this, with these two, the current given to us is 1 milliampere is the current given to us. Okay. Now he also said one word, saturation. When you look at the characteristics, saturation means here. This is saturation. VDS, ID. And if you see the forward characteristics, this is output characteristics. If you see it, transfer characteristics is called VGS versus ID. It starts from VT. So remember these two. For all this, we have an equation called ID is function of some constant k, VGS minus VT whole square. This is the basic equation required. Now what you need to know, ID is given 1 milliampere, K 900 minus 400 milli. VT is 400, VGS is 900, milli cancel. So K is of course 1 by 500. That's the value there. 1 by 500 is the value. Simple. Now what is this K? K is fixed for given device. For a given device that does not change. When it doesn't change, what happens? Now ID is equal to K into VGS minus VT square. Please remember K is fixed for a given device, fixed for given device, and VT is also fixed for given device. Now what is changing? Only these two are changing. As voltage is changing, ID is changing. That's why FETs are called voltage controlled device. Now substitute here. ID is equal to 1 by 500 into, what is the value of VGS given for us? He asked for us. He is asking for VGS 1400 millivolts. That means 1400 minus 400. So 1 by 500 into 1000. Okay. Square. Don't forget about square here. Oh, here also square is there. Don't forget about it. Why? Because 900 minus 400, 500 square. So if I say square here and square here, 1 by 25, 4 zeros and 6 zeros. Very simple. Because 1000. So 4 zeros and 4 zeros cancel. 25 and this. So this is 4 milliamperes. Why? Because this milli we have taken common. And that's why the option is, final option is D. The best way always you can take this milli and milli cancel and go ahead. So that's the final answer, 4 milli. Problem 5. Problem 5. Drain of N-channel MOSFET is shorted to the gate so that VGS is equal to VDS. The threshold voltage VT of a MOSFET is 1 volt. If the drain is 1 milli, drain current is 1 milli, for VGS 3 volts, then what is the ID for VGS 3? A. 2 milliamperes, B. 3 milliamperes, C. 9 milliamperes, D. 4 milliamperes. This is given in GATE EC 2004, 2 marks. So let me take you the equation straight away. VGS minus VT whole square. Okay. Now what he said was, we need to substitute here 2 minus 1 square. ID is how much given to us? 1 milli. Okay. Now K into 2 minus 1 is 1, 1 square is 1, so K is 1 milli. That's the value. Now ID is equal to, for the second case, ID is equal to K into 3 minus 1 square. What is K? 1 milli. 3 minus 1 means 2 square. So answer is 4 milli. That's why 4 milliamperes. So therefore the option is D. D is the option for this problem. Okay. Problem number 6. A mass capacitor using P substrate is in the accumulation mode. The dominating charge in the channel is due to the presence of A. Holes, B. Electrons, C. Positively charged ions, D. Negatively charged ions. That's given in GATE EC 2005, 2 marks here. It's such a very small thing, concept, but somehow they gave for it because maybe the concept is tough, they wanted to. So what do we answer for this? Here the option is very simple. First I am telling the option, that is holes. I will explain why it is so. So when you have a P substrate, for example, this is P substrate, and you have N here, okay. Now how is the accumulation of charges come? Suppose you have, when holes come, that means they got accumulated. We call it as accumulation. Okay. Accumulation comes with which? What type of voltage? The voltage we have is silicon dioxide layer. Silicon. So what type of voltage we have to give here? VGS should be negative. That's why when negative voltage is given, holes are developed, and that holes get accumulated with the substrate, which is P. That's why our option is A. Problem 7. The drain current of a MOSFET in saturation region is given by ID is equal to K into VGS minus VT whole square, where K is a constant or device parameter. The magnitude of the transconductance GM is given by, so we got A, B, C, D here, options are given. I am going to derive. GATE EC 2008. Now let me talk to you. For example, ID, he himself said VGS minus VT whole square. This is our solution for the problem. Now what is transconductance? Transconductance is generally given by dou ID by dou VGS. So 2 into K VGS minus VT by 1, because when you do this, when you do for this, VGS 1 comes. Therefore, what is the final answer here? 2K into VGS minus VT. That's the answer. That option is B. B is the option. That's all. Next, problem number 8. Consider the following two statements about the internal conditions in an N-channel MOSFET operating in the active region. Statement 1. The inversion charge decreases from source to drain. Statement 2. The channel potential increases from source to drain. See, which of the following statements is correct? A. Only statement 2 is true. B. Both statement 1 and statement are false. C. Statement 1 and statement are true. Statement 2 is not the reason for statement 1. D. Both statement 1 and statement 2 are true, and statement 2 is a reason for statement 1. Let's go to solution. Statement 1 is true. Statement 2 also true. But statement 2 is not the reason for statement 1. Therefore, option is C. The point is here, this is like a certain reason in the previous day. Now presently, it was earlier like this. So, it is also to say both statements are true, but this independently true. This is not the reason for it. Therefore, you should go for C is the option. Problem number 9. The source of a silicon Ni 10 power 10 per centimeter cube N-channel MOSFET mass transistor has an area of 1 square micrometer and a depth of 1 micrometer. If the dopant density in the source is 10 power 19 per centimeter cube, the number of holes in the source region with above volume is approximately A 10 power 7, B 100, C 10, D 0. GATE EC 2012. Let's go for solution. The area given to us is 1 into 10 power minus 12 meter square area. The depth is given for us 1 into 10 power minus 6 meter. Then what will be the volume? Volume is A into D. Then that is 1 into 10 power minus 12, 1 into 10 power minus 6. That will be 10 power minus 18. That's the meaning. So here is meter square meter, so it becomes meter cube. If you convert that into meter square, centimeters, it will become 10 power minus 12 centimeter cube. Converting meter cube to centimeter cube. That's first volume. We have calculated volume. Then the second thing that you need to know is, what is the value of N? N or Nd is equal to Ni square 10 power minus 12. And you know N into P is equal to Ni square. We call it as mass action law. In that, having note Nd, you can say P is Ni square by N or Ni square by Nd. That is, Ni square is, Ni is given as 10 power 10. 10 power 10 square by 10 power 19. That is 10 power 20 by 10 power 19. That is 10. That's all. So what we have, the volume is 10. 10 means what? 10 per centimeter square. Per centimeter square, if it is 10, what per total volume? This is per centimeter. So P, how much? 10 into 10 power minus 12. That is total. So that will become 10 power minus 11. So 10 power minus 11 is the total volume that you have, but that cannot be in an integer, 10 power minus 11. Therefore, our holes is equal to 0. Number cannot be an integer. Therefore, our option is D. Once again, look at the options. When you look at the options, 10 power 7, 100, 10, 0. So our option is D here. Problem number 10. In a MOSFET operating in saturation region, the channel length modulation effect causes A. An increase in gate source capacitance, a decrease in transconductance, a decrease in the unity gain cutoff, a decrease in the output resistance. Gate 2013. Channel length modulation effect. Let's go to solution. Most of the questions are coming on saturation region. This is called saturation region. What is saturated here? Velocity is saturated. When velocity is saturated, we call it as saturated region. Now, what is happening? What is finally affected? Because of voltage, if there is a channel length is modulated. Modulated means changing. Then finally what happens is drain resistance affected. Drain resistance is affected there. That's why we call it as option is D is the option. That's all.